live up to that introduction. So I'm actually here for one of the programs that KITP is running in astrophysics. So it's great to be here, enjoying interacting with colleagues from around the world on the particular topic. It's my pleasure to give a talk tonight. It's very informal, so please jump in if you have questions. Very rarely do I get to give a talk where people are drinking wine in the audience. I applaud that highly, so this is great. So my talk, yes, is going to be a wide range of topics. It's going to be a little bit about computer science, a little bit about mathematics, and a little bit about astrophysics. Not just about astrophysics, lots of things. So I thought I'd better start with a nice picture. Here's a nice image taken by the Hubble Space Telescope of a galaxy, the Whirlpool galaxy. And ultimately, theorists, observers, we're all trying to understand objects like this, its dynamics, how it formed, what its future is going to be. And I'm going to try to convince you that computers are playing a very, very big role in that process. So that's really the theme of my talk, the role that computers are playing in research in astrophysics. So as you know, I hardly need to tell you how much impact computers are having, right? We all know there's a huge impact on society. We're all glued to our devices. But of course, seriously, the devices we carry around, they're absolutely amazing. The change it's made is seismic in society and in what we can do with these devices. So you would think, well, that must have an impact in sciences too. Well, of course, the change and the revolution in the digital world is impacting science just as much as it's impacting everything else in society. So that's what I want to say, is what kind of changes are being made? It's a lot. In partially because computers are just getting so fast. So much faster over time, and I'll explain some of that. But in fact, most of the revolution is occurring because of software. The increase in accuracy and performance of software far exceeds the actual amazing growth in computer power. So the reason why we can solve such complicated problems today is mostly because of the development of more accurate and better and faster software. And I'll try to give you an example of that today. In astrophysics, there's a couple of really nice examples where software, smart ideas have really revolutionized how we solve problems in astrophysics, and that's all about software. But let me start with the computers. How fast are they? And how much change is there being? So to answer that question, there's a really nice data set, if you like, called the Top 500 list. There's a website you can visit called top500.org. This organization has been tracking the speed of computers since 1993, over 20 years. They've been tracking the speed of the fastest 500 computers in the world, where they use a linear algebra benchmark. They ask the computer to solve a linear algebra problem and measure how fast it does that, and that's how you get on this list, this list of the top 500. And every 6 months, they'll give a new list of the top 500 computers in the world at that time. So this is an amazing database to look back at, to see how things have changed. And this graph sort of summarizes this development over the last 20, almost 22 years now. So the graph shows performance in what are called gigaflops. These are floating point operations per second, how quickly you can add and subtract numbers, basically, in billions per second, versus years since 1993. And there's 3 lines shown. The bottom line, this yellow line, is the slowest computer, the number 500 on the list. The red line is the fastest computer, the number 1 on the list. And the blue is the sum of all the 500 computers on the list. And this is a log plot in the sense that this is plotted in decades of performance versus years. So a straight line in a log linear plot means exponential growth. So these speeds are going up exponentially in time. And they've been doing so for 20 years with no break in this trend, just going on and on. So this is fundamentally reflecting something called Moore's Law, which basically says every 18 months or so, computers get twice as fast. And this has been going on for well over 20 years. But the numbers themselves are also amazing. So back in 1993, the fastest computer was less than a teraflop, less than 1 trillion operations per second. Now we're into 20 petaflops for the fastest machine. Already the next machine has been announced, going to be installed in another year. It'll be 200 petaflops. So it's going to jump by another factor of a few. And we're well on our way to getting to exaflops. So teraflops are 10 to the 12, petaflops 10 to the 15, exaflops 10 to the 18. We're going to reach exaflops in my career very easily and beyond. And you know these are big numbers because these are numbers that are sort of like our national debt. So these are really, really big numbers, right? So we know things are really, really getting fast. So this is absolutely staggering. In my career, there's been more than a million-fold increase in the performance of computers. So that's really revolutionary what you can do with that. And it leads to sort of interesting anecdotal stories. One of my favorite, is very personal, is Mario, the name of a computer that was installed at a national supercomputer center made available to scientists for use back in 1993. It was Cray C90. There used to be a computer company called Cray that made computers. Cray C90, 16 gigaflops of performance, 4 gigabytes of memory, 130 gigabytes total disk space. Installed at the Pittsburgh Supercomputer Center. I was a new faculty member and used this machine quite a lot, getting a few thousand hours of time in this machine per year. Machine cost $35 million to install. And this exponential growth meant inevitably this machine was obsolete very, very quickly. Within only 3 years, the same center had installed a machine that was 10 times faster. At that point, it was no longer worth the money to pay for the electricity to keep this machine running when you had something that was 10 times faster and in fact used less electricity than this machine. So it just made no financial sense to keep it running anymore. So it was decommissioned in 1999, sold on eBay for $50,000 as living room furniture. An engineer somewhere in California who thought having one of these Crays in his living room would be kind of a fun thing to do. The machine was so heavy, in fact, that trucking it from Pennsylvania to California cost more than the $50,000. But that's the rapid state of progress. Every few years, these machines are going to go away. And of course, today, your iPhone is more powerful than this machine. So that's how powerful these devices are. You're carrying around million-dollar devices in your pockets, at least millions of dollars as of 10 or 15 years ago. It's really amazing. So where are we at the top of the list now? The world's fastest computer is in China. It's called Tianhe-T2, loosely translated as Milky Way 2. 30 petaflops of performance, peak performance, roughly 10 million times faster than your PC that you might have at home. So 10 million times more computational power than a single computer. The fastest machine in the United States is the second fastest computer in the world. It's called Titan. It's installed at the Oak Ridge National Laboratory. There's a very large computational science center at Oak Ridge. It's available to researchers across the country, open access to anybody who wants to use it by writing a proposal. Has 300,000 cores, so roughly 300,000 PCs wired together, 20 petaflops of performance. Consumes 8 megawatts of electricity to run this machine. In fact, the limiting factor in making machines bigger nowadays is their power consumption. If you wanted to make this machine 10 times bigger, you would need 8 megawatts, and that simply is unfeasible. You can't put that much power into a building, into a room. You can't generate that much electricity locally in one small room. And so the limiting performance now is the efficiency of the processors. We need to get them to be more efficient to be able to make them ever larger machines. But still, these are amazing machines that are available now for open use. Okay, so, sorry.
Computer cores, do you use similar to Intel's or something? Or?
This machine is a mixture of Intel cores and GPUs. This machine has, I think, 1,000 GPUs on it as well, and that's where much of the performance comes from, is from the GPUs. So GPUs meaning these graphical processor units that are now used to help accelerate computers. Yep.
What about the heat problems of running something like this?
Exactly. I mean, all that electricity goes to waste. A very, very tiny fraction is actually used for the calculation. 99.9% of it goes to heating the device, is waste heat. So in fact, it hurts you twice. You pay for the electricity to run the computer, and then you have to pay for the electricity to run this huge cooling system that consumes nearly as much electricity as trying to keep it cool. And so there's a lot of effort in trying to design efficient cooling systems to help reduce the cost that way. But it's sort of, you really have to hate to pay for it twice, once to do the calculation, once to cool the machine off afterwards. Yes?
Like in China and this one, who uses these? Is it just the government?
No, this machine is open science, so it's used for all fields of science and engineering. It's used in astrophysics. It's used in solid-state physics, fluid mechanics and engineering. They're using it for designing, doing aerodynamic calculations for design of cars and other things. So there's probably a few hundred groups that are given time on this machine through a competitive proposal process, and they just select whatever science they think is the most promising and they can use this hardware most efficiently. So it's one of the great things about computation in this country is that there are such facilities that are made available to scientists in general, and you can propose to use them. And not every country makes such computational power available to their research staff or researchers. Okay, so this is where we stand with what's available to use. But of course, the real problem is, how do you use it? I mean, you've got this great computer, but what are you going to do with it? How are you going to ever do anything with it? I mean, how do we harness these computers? Because let me go around to sort of a very low level of explaining, the issue here. Because after all, computers can only do operations on bits. They're very simple things. All they can do is take strings of zeros and ones called bits, and they can manipulate them. They can turn from 0 to 1 or 1 to 0, and they can do things with that. So bit operations can be combined into what we call algorithms. For example, you can do addition and subtraction, and you can do multiplication and division, or you can do logic. If this, do that, else do that. But still, addition, subtraction, multiplication, division, how do we get to astrophysics if all we can do is add and subtract numbers and multiply and divide numbers? I'll give you an example, for example, how you do multiplication with bits. So you have a bit string, zeros and ones, that represents the number 6. If you just left shift it, just take the same pattern and move it left, that turns into this bit pattern for 12. So if you want to multiply a number by 2, it's just a bit manipulation, shifting to the left. So that's a very simple operation. That's how you do multiplication, for example, in a simple example. But still, we're still at the problem of all we can really do is addition, subtraction, multiplication, division. How do we do higher complex calculus and mathematics? How do we do astrophysics problems on a computer? We have to reduce these problems to algebra problems. All we can do on a computer is algebra. So we have to figure out how to do higher mathematics in terms of just doing algebra. And so how do we do that? Well, that's the field of numerical analysis. There is a long-standing, very important field of applied mathematics called numerical analysis. The entire, if you like, job of numerical analysis is to find algorithms to approximate solutions to complex mathematical systems. So, for example, how does that work? Well, oftentimes when we're doing some mathematical problem, we need to represent functions, trigonometric functions like sine and cosine or exponential. Well, they can all be approximated using numerical analysis using things like series expansion, that's just adding and subtracting terms, or rational functions, and so polynomials essentially, and so on. So you can approximate these more complex functions using simple algebra. You can even do calculus. So we're going to get into some calculus here. We want to take a derivative, the rate of change of a function. Well, you can actually approximate the derivative just as a finite difference. Evaluate the function at some position x plus h, subtract the function at x, divide it by the difference h between these two places where you evaluate this function. That is an approximation to a derivative. And so you can even do calculus on a computer by reducing it to algebra, by doing additions and subtractions. Finite differencing essentially involves nothing more than additions and subtractions. So numerical algorithms can be developed to be able to use these computers. Yes?
You use the term approximation.
Yes.
Is that, as I understand approximation, or obviously in this you've got to have a precise answer?
Well, a precise answer, I guess define precise. We don't have to have a precise answer in the sense that what we really need is control on the error. We have to know the answer and how much error there is in the answer, or at least that the error is smaller than some number. And as long as the error is small enough, I'm happy. So if you tell me the error is 1%, well, maybe that's maybe not good enough, but maybe if it's 0.1%, okay, now I'm happy. Now I know my solution is accurate to say 0.1%. That's really all we can do with a computer, in fact. We can never get the exact answer because operations on a computer are not exact. They involve discrete numbers. You cannot represent every single number in the real axis. You can't represent every real number that exists. And so it's because you have finite precision arithmetic on a computer, you can never get exact answers. So we always have to deal with approximations. And that's why numerical analysis is so important, because it provides us with rigorous mathematical bounds on precisely what the error is in a numerical algorithm and how we can control it. And as long as we can control the error and understand what the error is, then I think we can make progress. We can understand whether the error is too big or too small, or whether we need to do better. That's really the key.
A good example is fractions. You can't do irrational numbers.
Indeed, exactly. You can't represent irrational numbers on a computer. And so if you do some calculation that involves an irrational number, then you're dead. You can't possibly represent it. Okay, so we've introduced the concept of numerical algorithms, and that's the key. To use a computer, the first thing you have to do is develop an algorithm that solves the mathematical problem you need, and then you can go to the computer and implement that algorithm and try to solve a problem with it. And so using numerical algorithms, we're going to be able to solve mathematical models. So let me give you an example. Let me use something concrete. So a simple example, the motion of some number of stars, some n stars, under the influence of their mutual gravitational interaction. So there's n stars, and they're all feeling gravitational pull from all the other stars. How do they behave? Well, this is not an esoteric question, because we see these objects in the universe all the time. These are called stellar clusters, for example. Here's a nice image of the Milky Way galaxy. The Milky Way is surrounded by hundreds of what are called globular clusters. Here's an image of a globular cluster. It contains roughly 1 million stars that are in gravitational interaction. They're gravitationally bound to one another. They're orbiting around a central common center of mass. And we'd like to understand the dynamics and physics of these globular clusters. To do that, we'd have to integrate the motions of these stars. Here's an example. Here's a movie where we've computed, we being Frank Summers, a colleague, has calculated the motion of 1 million stars in a globular cluster. If we could simply wait millions of years and watch globular clusters with our telescopes, this is what we would see. The stars in these globular clusters would be moving around in this fashion. At the center, they're moving very, very fast. Far away, they're kind of like a cloud of bees here buzzing around. Of course, since these timescales are so long compared to human times, all we see is a snapshot when we look with our telescope. We see the globular cluster as it is right now. What happened there? Well, we flew through the middle of the globular cluster and we out the other side, so you can see what was going on inside. So we'd like to be able to understand globular clusters and their dynamics over millions of years by doing these calculations. So what would be required? Well, what's the mathematical model to model a globular cluster? It's quite simple. It's Newton's laws of motion, F equals ma. But acceleration is actually a second derivative. Here comes back that calculus, right? So acceleration is the second derivative of position. The rate of change of position is velocity, and the rate of change of velocity is acceleration. So the rate of change of position is acceleration. So F equals ma introduces a differential equation, basically we call that. F equals ma is a differential equation we have to solve. So we're going to need some algorithm for integrating the equation of motion F equals ma. And I've kind of sketched for you how you can turn derivatives into algebra. So there are many algorithms we can be developed over the years to do this. Yes?
How do you set up the initial conditions for this? It's clear once you've started out everything moving, you can follow them.
So for that, you can use the observations. The observations can tell you the sort of relative positions of stars in an initial globular cluster. You can start with a globular cluster as we see it today, and then go from there. The positions are easy. The velocities are sometimes a little harder to get. Those you can get radial motions from Doppler shifts and so on. And in fact, what you can do is, in sort of the experimental style that Lars introduced, you can vary the initial conditions, try many different initial conditions, kind of like experiments, numerical experiments, and see how the resulting globular cluster dynamics evolves. Because you're right, it's very difficult to know precisely the exact initial conditions, meaning all the positions and all the velocities for all the stars. So you have to make some educated guesses and then see how the solution changes as you change your guesses. So here's our mathematical model, is this equation of motion. The force here is just the sum of the forces from all the individual stars. So on any given star I, you have to sum the gravitational force from all the other stars j. And I have to do that for every single star I. So if I have n stars, For each stars, there's n other stars, or n minus 1 other stars. And so it's an n squared calculation to calculate these forces. But still, straightforward. This is just, you can see, is just algebra, multiplications and divisions. So we have these two components, something to integrate the equations and something to calculate the force. But even in these very, very simple equations, when you're trying to solve them computationally, complications emerge. There's challenges here. Let me give you two of the important challenges here. One is that stellar motion is chaotic. This is another whole field of science. Perhaps you've had talks on this, on chaos and its importance. But one area where chaos comes up is in stellar dynamics. When you have more than two objects, then the motion of those objects is not analytic anymore, not calculable analytically, and can be chaotic. Here's an example. What does this picture mean? This is the interaction of three stars. And what's shown is the path of those stars through space. We started with two stars, a red and a green one, which are in orbit around one another. It's a binary system. So we have a binary star moving down, and it interacts with a blue star coming the other way. That's a third body, which hits this binary star. And so then for a while, you have these three stars interacting with each other, and you get this complete mess, complete gobbledygook, spaghetti of paths as these stars undergo these incredibly complex interactions. There's no analytic function you can write down that will describe the motion of the stars during this process. And then what comes out of it, this binary system gets kicked out one way, a little tighter together. You can see the circles are not as big anymore. The binary is tighter. It's gotten closer together, and this other star is kicked out with more energy faster from this interaction. And this can be chaotic because if I just change this angle of the incoming star by just a tiny amount, it's incredibly sensitive. The solution might be quite different again. So we have to worry about accuracy. This gets back to this question about accuracy. We have to worry that when things are so sensitive to initial conditions, how do we know we get the right answer when they're chaotic like this? And this is actually a really fundamental issue in science and in stellar dynamics. But I won't really go into it. Let me just say we have to worry about that a lot.
It's why the weatherman never gets better.
Right. It's the same reason, right? It's sort of this butterfly effect, indeed. So that's one issue about integrating the motion. The other one is just sort of a amount of work involved, a brute force issue. That is to say, remember there's this n squared scaling. That is to say, I have n squared operations to calculate the force. If I have n stars, I have n times n calculations to get all the forces. Well, if n is only 1,000, what we might call an open cluster, that's only 1,000 times 1,000, a million. That's a million operations. We can do that pretty easy. So we can do that direct summation. But if n is a million, like in a globular cluster, that's 10 to the 12 calculations per step. That's a trillion operations. That's getting hard. Our computers are only barely able to do that kind of direct summation today. And if you're talking about a whole galaxy with 100 billion stars, then n squared is 10 to the 22. Forget it. No computer for any time in the near future is going to be able to do a direct summation of 10 to the 11 stars in the future. And so we cannot use this brute force technique of just calculating the force directly. It's not going to work for studying galaxies or clusters of galaxies with hundreds of billion stars. How are we going to solve this problem? Well, we've tried to follow two ways. People have tried to build hardware that works. The so-called great hardware is a good example. This is already a very dated system. 64 teraflops, that's not that fast in today's world of 20 petaflop machines. They're 1,000 times faster than this hardware. But this is hardware that was developed by astrophysicists just to solve the force equation, to do direct summation of the force equation. It was quite successful for many years. It won many prizes, Gordon Bell Awards, for the fastest computers in the world for doing just this operation. It's now largely being replaced by GPUs and other accelerator technologies. So that's one way we've tried to do it, but I've already argued that won't work forever. Even with this fastest, specially designed hardware, you're still never going to be able to do a galaxy with 10 to the 22 operations. And that's where the algorithms comes into play, because what people realize is that, well, do we really need to compute the force from every single star when we're considering things like galaxies? Here's an image of the Andromeda galaxy. It's the closest galaxy outside the Milky Way you can see with your naked eye. It contains another 100 billion stars like the Milky Way. If I wanted to know the influence of the Andromeda galaxy on the Milky Way, I'd have to calculate the force from every star in the Milky Way by every other star in the Andromeda galaxy. That would be these 10 to the 22 operations. But do I really need to do that? Because after all, Andromeda is really pretty far away. It's 2 million light years away. Put that in perspective. Let me give you a picture in just a second. This is an example of using faster and better software to solve the problem. Not faster computers, not brute force, but using better software. And the software is called tree codes. And the brilliant realization was that, well, look, here's the picture of Andromeda Galaxy. There's a picture of Milky Way. You may wonder how I got a picture of the Milky Way since we live in the Milky Way, but I'll leave that to you. And this is to scale. This is roughly the size of Andromeda, roughly the size of the Milky Way in proportion to the distance to how far apart they are. And you can see that Andromeda is really a long distance away. And to calculate the force from every one of those 100 billion stars individually seems like a complete waste because they're all basically one object far away. The realization is you can just replace Andromeda with one particle whose mass is equal to the mass of all the stars in the Milky Way, and the force on the stars in the Milky Way is the same as the effect of this one particle with a mass equal to the total at the location of the center of mass of the Milky Way. And suddenly I've reduced the problem from having to do 10 to the 11 calculations to 1, just to get this one particle far away. And that's the brilliant idea that underlies tree codes. When objects are far away, when groups of particles are far away, you don't calculate their forces individually. You just calculate the effect of a sort of a superparticle that represents the combined effect of all these particles at the center of mass on the particles that you're interested in far away. And so I have a slide which sort of shows how this works in detail. I won't try to go through in detail, but I'll just tell you, like, if you're at this particle here on some grid with each dot represents a particle, you're here, you want to calculate the force from these particles, well, they subtend a large angle. They must be nearby. So I have to do direct summations to get these forces accurately. We're back to this accuracy issue. To do this properly, you do have to do direct summation because this approximation of a single particle won't work there. But for the particles way over there, they're so far away that you can use this approximation accurately. They subtend such a small angle. I know they're very far away. I can just replace them with 1. And so the brilliant thing is it takes this n squared algorithm and turns it into something which is n log n. And log, base 10 log of 10 to the 11 is 11. And that's 10 to the 10 times smaller than the actual number n. So this is a huge saving. This is a saving of 10 to the 10. Again, no brute force calculation can compete against the savings you get from using a smart algorithm. So the key here is that the algorithms of what revolutionized what we can do with these computers, not just the fact that they're so much faster. These algorithms allow us to do things we could have never done before, like merging galaxies. We can actually calculate from first principles the interaction of two galaxies as they collide with one another. You may have heard in the news, Milky Way and Andromeda is going to collide in another 2 billion years. How do we know, what's going to happen with that interaction? Well, we compute it using tree codes. We can calculate the interaction of two disk galaxies, Andromeda and Milky Way. You can even have different kinds of stars. Young stars are blue. Old stars are red. They're both disk galaxies, and we'll just watch this interaction proceed as these two galaxies orbit each other. They're on an orbit which merges. You can see how thin these galaxies are as you rotate around. As they get close to each other, the gravitational pull becomes very, very strong. The galaxies become very tidally distorted. They throw off some outer reaches of the stars in so-called tidal tails. The nuclei become bound together. On a second passage, they fall back together. You get another splash of stars in the second interaction, and then more interactions, and you end up changing the galaxy properties pretty dramatically. You start with these two disk galaxies, and you end up with one elliptical galaxy at the end. Over the course of billions of years now, in this particular case, this interaction has occurred.
And yes? None of them touch?
None of them touch, because the size of the star is absolutely minuscule compared to the overall. That's right, exactly. Yep.
Does this deal with the spin alignment question?
Spin alignment question?
Of the merging galaxies, apparently they adopt some preferential spin.
As they merge, you mean, or?
Yes, I've read something about that in the last couple of years.
I'm not an expert on galaxy properties, and so I'm not aware of the spin alignment issue here. I do know that these kind of merger calculations have been used to sort of model the property of small elliptical galaxies, and it works very, very well. Both in terms of the properties of the stars that are left behind. You see, mostly the red stars get stuck in the galaxy, and as well as various other properties. So, my simple answer is probably yes, because it seems to work so extremely well. Yes.
We're carrying this out for, say, billions of years.
Yes.
What's your time step? Several 100,000 years?
So in these yes. Let me just say the total number of time steps you might take would be a few 100,000. So I guess doing your sort of tens of thousands of years, maybe 100,000 years is the largest time step you get away with. That's right. That's right. So that seems like an incredibly long time, but that's the dynamical time. So your time step has to be smaller than the smallest time scale you're trying to resolve in the problem. And that'll be the orbital time near the middle of the galaxy. So you have to resolve the motion of the stars in the center. In fact, you do very sophisticated things. You don't take the same time step for all the stars. The stars that are moving rapidly, you take small time steps for. The stars that are moving slowly, you take much longer time steps for. And then you find a smart way to combine the calculation using all these different time steps. That saves you a tremendous amount of work. And so, you make sure your time is small enough to resolve these. Okay. Yep.
But you're saying nobody touches. I mean, so the separation is significant enough, and
Yes.
the gravitational pull small enough that the impact on any given star system is relatively minor.
On any individual star itself,
Right.
like the sun, for example, when the Milky Way finally merges with the Andromeda, yes, exactly. So if you're investing for 2 billion years in the future to know what to worry about,
Right.
the sun has essentially a zero probability of colliding with any other star in the Andromeda galaxy. That's because its cross-section is so tiny compared to the volume of space filled by the Andromeda galaxy that the chances of it hitting anything are absolutely minuscule. Yes, I mean, that's again showing...
Observationally, from our point of view, we'd see almost nothing.
Well, this is what you would see. It'll be happily very dramatic because, remember I showed you the picture of the Andromeda galaxy before.
Right.
Imagine that across the entire sky. It'll be visible... the galactic center might be visible in the day. It'll be so bright because it's so close. I mean, it'll be absolutely spectacular as it's happening because you'll see this entire other galaxy right on top of you. And then as this interaction proceeds, you'll see a Milky Way that's highly disturbed with lots of star formation and other things going on. It'll be a very dramatic and very, very beautiful event. If only we could, sit around for a billion years and watch it go by.
But it change our climate.
It could do many things, yes, right. Maybe that's a good thing.
Burn out way before any of this red giant.
Sorry?
Our sun's going to burn out.
Exactly right. In 2 billion years, it's exactly right. Exactly.
Yeah, we're history anyway.
Right. So.
I don't care how far we can travel.
Right. Exactly. Yes.
If you're colliding galaxies, you must really move macroparticles, each one representing a million stars.
That is absolutely right. So because these calculations still do not reach a billion or 100 billion stars each in the galaxies, then there's only a few 100 million particles in each one of these galaxies, and therefore each particle doesn't represent one individual star, but rather a collection of stars. And to be a little more technical, then you're just sampling phase space with these particles, and you're essentially solving the Boltzmann equation using a particle method to sample the distribution of stars. You're absolutely right. But nonetheless, the dynamics is, this gets back to error control. Since we're not doing individual stars, how do we know that using macroparticles is okay? Well, again, we have quantitative error bounds, and we can ask how much mass resolution do we need to get the right answer. And some things are resolved, and to be honest, some things are not resolved. Some things about these calculations are not correct. You can't answer. There's some questions you cannot answer by these calculations because you don't have enough resolution. They're not accurate enough to measure some quantities. And so that's part of the game, is figuring out what you can believe and what you can't believe. What you can learn, what you can't learn. Not believe, I should say. So there's, I thought, a good example of stellar dynamics of how you turn a computer, a very, very fast computer, into something you can do real astrophysics with. I was going to give you another example. My time's running out pretty fast, I think. So I'm fine. Okay, so then, because my title involved accretion as well, I better get to this. I've done the merging galaxies. Now I better do the accreting black hole. So it turns out that we've discovered observationally that there are black holes at the center of galaxies. And the best example is our own Milky Way. It's got the best evidence for a supermassive black hole center of galaxies comes from our own Milky Way. And so we know that there's a few million solar mass black hole in the center of our Milky Way. And these galaxies, or these black holes at the center of galaxies, they can do very interesting things in some cases. They can produce very powerful outflows and jets from so-called, when they're embedded in things called active galaxies. For some reason, these black holes can become sort of active and produce outflows and emission. This has happened in the Milky Way in the past because we can see evidence for these huge bubbles that have been produced by the black hole in the past in the Milky Way. And we can see it because we can look at other galaxies. Here's a galaxy called Centaurus A. And if we could see Centaurus A with radio eyes, we would see these colors of radio emission being produced by a black hole at the center of the galaxy, which is ejecting very powerful jets of plasma, moving at nearly the speed of light into the intergalactic space. You can see that Centaurus A looks like a disturbed galaxy. It doesn't look like the Milky Way galaxy. It's because it's probably undergone an interaction, like I showed you just before. It's probably the end product of that kind of calculation I just showed you. And that's what's energized the black hole at the center of this galaxy. So, yes?
Is that Hawking radiation then?
This is not Hawking radiation. This is plasma produced by regular plasma dynamics as opposed to more exotic things that produce Hawking radiation. This is just plasma physics happening near the location of a black hole. And so that's the key. How do we know what this is? Well, to answer that question, we have to address the issue: what happens if you have a black hole? It's surrounded by plasma, by gas made up of ions and electrons. It's ionized particles, and this gas is falling into the black hole. What happens for that in that process? This is a simple question to ask, and requires a very, very complicated mathematical model to solve and answer that question. Why? Because as the gas falls in, if it has any rotation, it begins to spin up faster and faster. Just like, again, if you've watched the Olympics, when these figure skaters pull their arms in, they spin fast due to conservation of angular momentum. Well, as this gas falls in, it starts spinning faster and faster and faster. It makes a rotationally supported disk. This disk orbits around the black hole, and this disk is responsible for producing, we think, these jets of emission. We'd like to understand the dynamics of this disk of plasma produced around a black hole as it falls in. To do that, we have to model the plasma dynamics, the motion of the gas around the black hole. To do that, we have to solve the equations of magnetohydrodynamics. I'm not even going to attempt to try to write all those down, but there's a well-posed system of equations that describes the dynamics of plasmas that can be turned into a numerical algorithm for solving the plasma dynamics. And this is what happens when you take a small piece of plasma orbiting around an accretion around a black hole. There's an instability associated with the magnetohydrodynamics, with the magnetic fields produced by currents in the plasma. There's an instability that produces turbulence in the plasma, and this turbulence has very important consequences. It ultimately produces angular momentum transport. It allows angular momentum to move outwards in the disk, allowing matter to fall in, and moreover, it produces these jets at the center. The interaction of the magnetic field generated by this instability with the spinning black hole can make a jet. And so we go from a sketch, a cartoon of what things might look like in the previous slide to what they actually look like. It's really quite exciting. In the last 10 years, last 5 years really, we've gone from artist's sketch to, I'm going to show you a movie now, of an actual general relativistic MHD calculation. General relativistic meaning you're doing the full general relativity of motion around a black hole using full MHD to calculate the plasma dynamics. And then we're going to compute images using the appropriate ray tracing of photons that are curved by space-time around a black hole to see what that looks like. We're actually able to follow the motion of this plasma as it falls into a black hole. We start off with a disk here. Here's the equator of the disk. We're going to fly around this pole. So there's a black hole that's spinning, producing jets in the vertical direction perpendicular to the disk. You can see the jet there. We're going to fly over top of the black hole now. And this is not an artist's impression. This is the plasma dynamics being calculated in full 3D along with this radiation transport algorithm to compute the images. As we fly over top of the black hole, this jet's going to come moving around towards you. It's going to poke you in the eye in just a second. It's become very, very bright. You can see See the conical shape of this thing here? Here's getting closer and closer to the pole-on view. There it is, pole-on. You're looking right down the throat of this jet. Now you're past the edge, and now we're going to fly into the very inner edge of the black hole, where all this motion, this orbital motion of the plasma, and all this turbulence is being generated by this instability I showed you before. And now we begin to see GR effects. You see light bending effects producing weird, shapes to the disk. You can see the back of the disk because photons are bent around the black hole. And then when we fall in the black hole, everything stops. It's all over. But it's there you go. So to me, it's an amazing calculation because it's not an R suppression. It's the solution of the actual dynamical equation for the plasma along with the actual rate of transport. It's a very, very impressive calculation. So let me finish up with. Oh, sorry.
Well, you mentioned things falling into the black hole.
Yes.
I have always thought that things did not have any way of avoiding being sucked into a black hole, and I just what's the?
You're absolutely right that some fraction of the stuff has to go in, but as it's falling in, if there's some way it can give energy to the other stuff coming behind it, you can push on it. If you can push on it hard enough, you can push some of it away as you're falling in. And that's exactly what's happening. But how do you push on it? Well, that's where the magnetic field comes into play. Because the magnetic field can connect you falling in with your friend far away. And using the magnetic field, you can transfer energy from you to your friend. And if you can give them enough energy, then you can send them off away. That's exactly what happened. There's a small fraction of the plasma gaining energy from the magnetic field and being driven outwards, while most of it's falling into the black hole. And that little bit that's being flung out is enough to produce these jets and emission and so on that we see from green black holes.
Forward motion creates an equal motion, or is it completely different?
Yes, because it's in full 3 dimensions and there's rotation. So the motion is not just along a line. It's very, very complicated and it's turbulent flow. All you really need is this net energy transport from some fraction of the gas to some other fraction of the gas. And if you can give it enough, you can get it to leave the system. That's the way it works.
So that's really a product of the accretion disk itself.
Exactly.
It's not coming out of the black hole.
That's exactly right.
Per se.
It's before it ever gets in. It has to. If it goes in, you can't come out again. So you got to get the stuff flowing in the jet before it crosses the event horizon, goes into the black hole. Exactly right. Exactly right. So it's important to, I think, realize that, again, that I've tried to emphasize that the key element here is the software. I think that the computers are fabulous, but if you don't have the computer codes to solve these equations, you really can't do much with it. So where does the software come from? Well, scientists write their own codes. And that's really a major bottleneck because it takes a long time to develop these codes, and you have to be an expert in software engineering and computer science. These computers are not easy to use. They're highly parallel systems. To use them efficiently requires knowing a lot about parallel programming. It's not something that scientists usually get trained in undergraduate. This is really quite a big bottleneck because we don't have sort of experts in computational science necessarily, also experts in astrophysics at the same time. But this is the world we have. This is what we have to deal with. Why don't we just buy software? I mean, after all, there's tons of commercial products. But the answer is because if you can find a GR-MHD code available for sale, I'll buy it. I don't think you're going to find a GR. We got to write your own code from scratch, and so it's because we're solving problems that are not generally solved in the community, in the business community, and so we have to write our own codes. But still, I think building codes on modules that already exist is extremely important. Sharing software elements, sharing modules is the way to build for the future. So you can build if you ask every student to start from scratch and write a code from the beginning every time, it's not going to work. You can never progress more than a certain distance. So if you want to go on, you've got to build on what people have done before, and that requires so-called community codes, building codes that others can build on top of that. In fact, Lars didn't mention it, but actually one of the best examples of community codes is here at the KITP. Under the leadership of Lars and a few others, they've built a really wonderful code for stellar astrophysics, for solving the equations of structure for stars, called MESA. And they've made this code freely available. You can download it, the software for free. You can build upon it. And so this is a prototypical example of the way that code and software development needs to be done in the future, where it's completely open source. Anybody can adopt it and use it and build upon it. And so I think the community is moving in those directions, and I think it's very, very important that we do that. So again, if you Google MESA, you'll see this great website, and you can learn a lot more about what Lars is doing in his other life. Okay, so I'm pretty much done. What's the future? I think it's extremely bright. I think that inevitably the hardware is going to keep getting faster. I see no end to this exponential curve. There's no break in that power law. It's going to keep going. And so we have to plan for that. We have to plan for computers that are 10, 100, 1,000 times faster over the next few years. And that's going to allow us to tackle even bigger problems. What we need is better algorithms. It's always about developing algorithms to solve complicated equations. We need better community codes and visualization software so we can see what's going on and understand it. Adding more physics in to be able to understand more complicated problems. At the end of the day, it's really about training scientists and students in particular to learn how to program. I mean, there's actually a real problem right now in that students don't learn how to program computers anymore. They use apps, and apps don't require any knowledge of how you program at all. And so if you want to be able to use these computers and program them, we need to be able to train students in how to program and how to be able to use these machines effectively. And I think it's incredibly important because all the most interesting problems, I think, are going to be solved computationally. That's really the future. Okay.
How are they going to solve the electricity problem?
So, excellent question. So, scientists don't drive computer architecture. We get whatever the market drives. So that's why we're using the Intel processor on these big machines, because Intel sells it in their PCs, and that's where so if you think about it, what's driving architecture design nowadays? Well, it's your smartphone again. And what's a limiting factor for a smartphone is power. The longer you can keep a smartphone running, the more people will buy it. It's a big attraction. So power-efficient processors are a big thrust in computer architecture right now, which is why we're going to be able to do this, because Intel and other manufacturers are going to develop much more power-efficient processors for the mobile computer market, and we're going to use those and those designs in these huge computers and reduce the power consumption by orders of magnitude. So that's why it's going to work.
And Jim, you touched on it, but the whole GPU thing, the graphical processing thing, caught everybody by surprise. That came out of gaming, right?
That's right. Another example where there's a huge market of kids playing games in their basement and making those things really cheap because they sell so many of them.
We don't have basements in California.
Yeah. Okay, there you go. Garages.
Princeton has basements, we have garages.
Right. So that made these GPUs really, really cheap because they sell so many of them. If you can figure out how to use them, and you've got this really, really cheap architecture to use. So you're right, that GPUs were a bit of a surprise and have been used quite effectively in some examples.
Yeah, early on you were talking about the effect of chaos, like even with three bodies. So
yes.
Chaos means that small errors will have large effects in the end.
That's right.
So you've got like two galaxies, 100
That's right.
bodies. Are you actually capable of showing what the errors is, or is what you simulate is one possible outcome out of many?
That's correct. First of all, it depends very much on the initial conditions. Exactly right. The other thing that when you know your system is chaotic, then you must give up the notion of being able to predict the exact positions of all the stars at any time in the future, because that's simply impossible. All you can do is predict statistical properties, because those things become independent of the chaotic nature. So rather than knowing where each of the individual 10 to the 11 stars are after 1 billion years in the future, we simply ask what's the distribution of stars rather than what one individual star is doing. And those kind of quantities, there's many statistical properties that are well converged and are independent of the initial conditions. And those sorts of things you can get handles on. But the only way to know is, you're absolutely right, you have to do ensembles of calculations, and you have to worry about studying this in a statistical way rather than sort of a deterministic way where there's only one answer for one initial condition.
Is the chaos localized? Like say, if you look at a micro level, there will be a lot of chaos, but if you look at the overall picture, it will pretty much...
I think that might be a good way to describe it. Again, I'm not an expert in stellar dynamics, but yes, that's I think individual stellar orbits can be chaotic, but the overall galactic, for example, the motion of the two galaxies is not chaotic. That is very predictable. That follows very simple rules. But in individual stars in those galaxies, that could be very chaotic.
I wrote my first computer program in 1960 in binary.
Oh my gosh.
I'm not surprised that computers have speeded up since then, and will continue to do so for a while.
Mm-hmm.
But I don't share your confidence at all that this is kind of going on and on
Forever.
and on. I mean, absent quantum computing, I think there are real physical limits to how much faster you can go, and you seem to deny that, and I wonder why.
I think, of course, we can't go forever, because that would, we're going to get infinity if we try to go forever. And in fact, we've already hit limits. I mean, let's be honest. It used to be that every year the clock speed would go up. 400 megahertz, 800 megahertz. Processor speeds have been stuck at around 2 to 3 gigahertz now for like 4 or 5 years, and they're probably never going to go up anymore. We've hit a limit, and that limit is precisely the kind you're talking about. It's how small you can make the circuits and how much power consumption you need to drive it. And at 3 gigahertz, you're at the limit of the break-even point. But what you can do instead of making it faster, is come up with some other idea. What the other idea is, people are adding more and more cores. So they're changing the design of the processor to be able to add more functional units, more things that can be going on. Makes it more parallel, it makes the algorithms different, it makes the way you use it different. But at the end of the day, it still has more flops per watt of power than it did the year before. So I think we've got a long way to go. Another probably factor of 1 million to go before, and okay, I'm happy with 1 million. It's not forever, but I'll take the 1 million. I think there's still a ways to go yet.
In your example of the globular cluster and of the colliding galaxies, your codes were really particle pushers.
That's right.
But an alternate method might be to introduce not individual stars or even macroparticles, but a gas of stars.
Right, a mesh.
Put it in a space mesh
right.
and use fluid equation.
Yep.
Is that a viable?
Yes, absolutely. There's intense research now in so-called mesh methods. So it's not really a fluid because these are still collisionless systems, and so the relevant underlying equation is the Boltzmann equation. But you can discretize the Boltzmann equation either using particles, which is what these approaches use, or you can use meshes. You can discretize velocity and space in terms of finite elements, finite grids. And there are many mesh codes for solving Vlasov equations. They have their own limitations and their own problems, but right now they're under intense development, and they look very promising in the long future. So the other thing that's going to revolutionize, not only do we have another factor of 1 million to go in processor speed, but I suspect we have another 1 million to go in accuracy of algorithms. And maybe these mesh methods, when they're fully developed, will end up being much, much better than particle methods. And for the same computer power, be able to do much, much more bigger calculations. We have to wait and see. But there's much, much more development to go in algorithms before, which also makes this exciting.
So I think we should stop. This is a good point to stop. Thank you very much, Jim, and I'm sure I'll stay and take questions.